All right, you guys need to make sure that before we start 6-6, you're okay with the word rational. So that when I start throwing out, is this a rational number, you're okay with it. When you guys first started learning to count, you started using whole numbers. Then you started putting negatives in front of them. So then that became integers. Positive and negative whole numbers are integers. Okay? Then, when you started looking at the space in between them, you started coming up with numbers like 2.5 or -3/4, things like that. Anything that can be written as a fraction is a rational number. Anything that can be written as a fraction is rational. Okay, so rational. Anything that can't be written as a fraction is irrational, like pi, or the square root of 7. Things like that, negative square root of 7. Those can't be written as fractions. Non-repeating, non-terminating decimals cannot be written as fractions. 2.5 can be written as a fraction. Okay, that's a terminating decimal. 1/3 is 0.3 repeating. That can be written as a fraction. So a terminating or repeating decimal is rational. Irrational numbers can't be written as fractions. And then, of course, certainly you have imaginary numbers, positive or negative imaginary numbers. So irrational, rational, and just look at which of them are, and imaginaries. Okay. The rational zero theorem is going to find if you have any rational zeros, it'll find them for you. So if there are irrational, it's not going to find them. If there's imaginary, it's not going to find them. Okay? Only rational. Okay, so to help you guys out, looking at the two methods that you guys know so far, solving by factoring. So 3x, x, so I'm trying to put this in a context that you guys already know. Things that multiply to give you 10. How about 2 and 5? I'm going to make that one plus, this one minus. Let's check the outside. So there's 15x. Check the inside, minus 2x. And you get 13x for the middle. Now to solve this, I need to set this thing equal to 0. So 3x minus 2 is 0. And x plus 5 is 0. So add the 2, divide by 3, 2/3. Subtract the 5, -5. So those would be your two answers. To put it in the context of solving with the quadratic formula, to ground you guys and let you see that this is working, before I just jump in and do the rational zero theorem out of the blue. X is equal to, so that would be the opposite of b, plus or minus b squared, so that would be 169, 13 squared, minus 4 times 3 times -10, all over, twice a would be 6. So x is equal to -13 plus or minus. Type that in your calculator, and I think you get square root of 289 over 6, which I believe, honestly, I can't do that in my head. I did it ahead of, whoops, square root's not there anymore, yikes. I believe the square root of 289 is 17 over 6. So -13 plus 17 is 4, 6 is 2/3. So there's one of them, check. And -13 minus 17 is -30 over 6 is -5. So there's the other one. Okay? So I'm trying to prove to you, show to you that it actually works. Alright? I'm going to get rid of a little bit of this so I'm not crowding myself too much there. Now, the first thing that you guys need to do when you set up the rational zero theorem, and I'm not explaining why this is working right now, just how to do it, is you have to write all the factors of the m number. So that means any number that can be divided evenly into that number on the end. So positive or negative all of these numbers over all of the factors of the front. So that would be a positive or -1 can divide into 3, and a plus or minus 3. Now that's the setup to find the possible rational zeros. I'm going to stress the possible ones. If you could have a rational zero, it's got to be in this list. Now what is this list? If everything was all over 1, I'm trying to scribble this out virtually, just shh, okay, don't look at it. Then you have all of these numbers over positive or negative 1. Well, that just means that it's plus and minus 1, 2, 5, and 10. Let's scribble out this one now. If they're all over positive or negative 3, then you also get plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, or plus or minus 10/3. Again, I haven't told you why this is working yet. That'll come. Right now, I'm just doing the setup. If you're going to have a rational 0, it has to be in this list. Okay? Now, what you have to do is then you have to graph it. I'm going to pull these over and cover this stuff up a little bit. I've graphed them. And you look at your graph and you go, check this out. You're looking for the zeros. I wanted a pen. There we go. And I've taught you guys before, zeros, if they're real, show up as x-intercepts. It has to be in this list. Well, check it out. There's a -5, and there is, now I can't tell from this graph, is that 3/4? Back to before. Is that 3/4? Is that 4? Why is this always doing this? I'm starting to get really frustrated by this. Okay. Is that 4/5? Or is it 2/3? And that's what this does for you, is it finds it for you. You also have to, let me pause this. Alright guys, they're done vacuuming the room, so let's see what I can do. Okay, so what the rational 0 theorem does for you is, sure, you can see whole numbers easy enough, but the fraction ones, those are the ones that get difficult, and that's why you need this list, is so you can pick out the fraction ones. Now, being able to see this here doesn't guarantee that the sucker's actually working. What you need to do is, where did it get lost? Maybe it's underneath this. Let me go back. Let me pop this down. Let me pull this over. Yep, there it is. Okay, is you have to go to your table and actually enter the values into your table to see that they actually work. And there, 2/3 and -5 are giving you 0. So you have to verify. Once you visually find them, you have to verify them in your calculator that they do indeed give you 0. Because sometimes these suckers are really close together and you don't know. Is it 2/3 or is it 3/4? Sometimes they're both an option, so you have to type them in. If it doesn't give you 0, it's not a 0. Alright, here's the big old rational 0 theorem. This is everything you're supposed to do. I can let you guys read it more thoroughly, but the first thing you have to do is list what are the possible zeros, which are the factors of the last or the factors of the first. I did that, and I'll go through it again for you. Then you graph the sucker on your graphing calculator to narrow down the choices from step 1. And I'll talk more about double zeros later on. With your table set to ask, we can work on what that means. Enter your refined guesses from this step and check and see if they are indeed rational zeros. Okay? So here we go. First thing you have to do is write out the possible rational zeros. So it's all the factors of 24, so plus or minus 1, 2, 3, 4, 4, 6, 8, I don't know what that was, 12, and 24. Oh, there's my 4, my lovely 4s. Okay, all over all the factors of the front. So plus or minus 1, 2, 3, and 6. Okay, technically what you're supposed to do is go ahead and rewrite this sucker because they're all over 1s. So I know this is tedious, and I'm not going to do it for the second one, the one on the next page, because of the interest of time. I'm just being very thorough here, and I'm going to punch this thing. Okay, being very thorough. Plus or minus 6, 8, 12, whoops, forgot the plus and the minus, and plus or minus 24. Woohoo, I got one. Okay, now if they're all over 2, I'm going to generate a half. 2 over 2 is 1. I already have it. Don't list it again. 3 halves. Then plus or minus, that would be 2. I already have it. That would be 3. I already have it. That would be 4. I already have it. That would be 6. I got it. And 12. I already got it. So don't list it again. Now go to thirds. Plus or minus 1/3. Plus or minus 2/3. Plus or minus, let's see, that would be 3/3. I got it. 4/3. Oops. Oh. What is it with that? I mean, I know my penmanship is bad, but good grief, people. All right, 4/3. Plus or minus. Okay, where were we? 6/3, I got it. 8/3, which would be 4/3. Oh, no, 8/3, that's right. Sorry, I don't already got it. 8/3. Okay, and then 12/3, I got it. 24/3, I already got that. Okay, so then you gotta go to sixes. Plus or minus 1/6. I know it's a long one. 2/6 is a third, 3/6 is a half, 4/6 is 2, there's 6/6. So those are already there. Okay, then you have to graph it and look. I guess it's big enough I could have stayed there. So it looks like -1, 2, 3. So possibly -3 might work. I need to check and verify. Okay, if I were to be a betting man, I bet that's -1/2. I can verify that in a second, see if it works. Then that, okay. I'm not sure if that's 1.5 or if that's like 1 1/3. This is where you look back at your list. Okay, 1 1/3 would be 4/3. Yes, there is a possibility it's 4/3. 1.5 would be 3 halves. And yep, 3 halves is there. Okay, doesn't mean they both work. It's just saying if it's there, I need to check and make sure. So then -2. Then what you have to do is you have to enter those values into your calculator, into the table, and see which one would work. 1.5 doesn't work. It's 1 1/3. I've already checked it. If you typed in 1.5, it's not going to come up the right value for you. It's going to come up with something other than 0. So I typed these in and narrowed it down for that. I wish I could do this dynamically, but I can't type this thing in and have it show you because this doesn't support it, and I apologize. That's a downfall of using this software. Okay. When you have questions on that and how to set your table up, I'll be happy to go through and show you how to do that. Okay. If you need to see it again, I'll just zip through this one really quick. Plus or minus 1, 2, 4. Oh, one of these days, I'm either going to get new penmanship or new software. I don't know which it is. 4 plus or minus 5 plus or minus 10 plus or minus 20 all over, then all the factors of the leading coefficient, plus or minus 1, 2, 3, 4, 6, and 12. Jiminy Christmas. Whenever you guys see a 9, how about we just say it, they're 4? How about we just relearn it? How about that? 4. Okay? Then you're supposed to write them all out as fractions. But again, in the interest of time, trying to just do it. I guess I didn't. I had it big enough. So that looks like 1, 2, 2.5. -2.5 is a possibility. -1/2. Somewhere near there. Ooh, that's tough. 1/3. And 1, 2, 3, 4. Okay. Now, like I said, I've already gone and typed this thing in to see what works. Let's see if I can pull that thing out and see which ones it is. So there you go. It was the 3rd. I got it right that day. Got it. I guessed I'm good. Now, if you're typing these in and you're coming up with, let's say, you think that really looked like a quarter, because there's a quarter, and you type in a quarter, it would come out as 0.25, and let's say it gave you 17 as a y value. It's not a 0. It doesn't mean that you're a failure. It doesn't mean that, you've done something wrong. It just means you need to refine your guess a little better by going back and looking at the list. You know what? Maybe it's a 1/3 instead of the quarter. Okay? So that's the rational zero theorem. You write the list of possibles, you graph it, you look at it, you pick from the list, and then try them on your table to verify that they're actually giving you zeros. Okay, I think that's the last screen. Can't believe this actually finished.